there are many situations where products have sort of nice geometric interpretations because if you interpret two quantities as lengths, the product of those two quantities counts as an area, and you can draw a picture of that. The product rule for derivatives is a really good example of this sort of situation. So if we start with two quantities that we interpret as lengths, so maybe let me call it f and g, and you let these quantities change a little bit. So if these quantities are both functions of time and you let them change a little bit, right, f might change a little bit, and so this quantity would be called, I guess, df. G would change a little bit when time changes, and so this little change in g would be called dg. So what about the change in the area, right? The area in this situation is f times g. So the change in the area, which I guess we should call d area, is df times g. And let's see what the change in area is. So if we find the area that's represented by the product of these two extended lengths, right, we have to sort of make our box a little bigger here. This piece on top, it's f across the bottom and dg high. So the area of this top piece is f times dg. The area of this right-hand piece it's df wide and g units tall. So df times g. And then this little bit in the corner is df times dg. But remember, when you have two differentials multiplied by each other, that's sort of doubly infinitely small, and it's so small that we can neglect it. So we'll ignore the df dg. Right? Really, if we take what all of this d stuff is a shorthand for some sort of limiting process. And when I say this part is doubly infinitely small, so it's 0, what I mean is if you do this properly by taking a limit as these changes go to 0, this part, the limit of this part is 0 itself. So okay, so back on track. Using this diagram, the change in area, so the little change in area is just these extra pieces, right? This piece and this piece. We don't want to count the big chunk in the bottom left because that's what we started with. We only want to add up the changes in the area. So that is the new area that we've accumulated. So the top piece is f times dg. And then the right-hand piece is df times g. So we get df times g is f times dg plus df times g. And then if you, right, we said everything was a function of time here, so if you divide everything by dt and do the sort of fraction arithmetic or fraction algebra to get your dt's placed like this, well, now this looks like the product rule. So the product rule for derivatives has this really nice graphical explanation for why it is what it is, or graphical interpretation, I guess, would be the right word. So let's see if we can come up with the same thing for integration by parts. So remember, integration by parts is the integral of u times dv is u times v minus the integral of v du. And I'm going to use the definite integral version of this. So we're going to have bounds, but these bounds, right, in this situation, u is really going to be a function of time, and v is also really going to be a function of time. So these bounds are actually time values. So that means we need bounds here from time a to time b, and on this integral from time a to time b. T equals b. There we go. Okay, so if u and v are our quantities, then maybe what we should do is draw a picture in the UV plane. Now we're going to have to be a little careful because time does not show up on this, does not show up explicitly in this coordinate system. Only u and v show up in this coordinate system. But we can partially draw a picture of what happens when time goes from A to B, because we can make a moving point, which is really called a parametric curve, a moving point by building a point out of these two functions, so u of t and v of t. So when time is at the beginning, so A, we're at some spot here. So this would be, the u value here is u of time A, and the v value is v of time A. And as time goes on towards B, this point is going to move around the plane until it reaches some other spot. So let me make that curve a little nicer, a little more reproducible. So when time gets up to B, maybe we're over here. So u of B and v of B. Now I've drawn this as if u and v are both increasing functions, but they don't have to be. Right? Okay. So now that we have a picture of sort of the setup of these functions, let's interpret each one of these integrals in terms of this, this diagram. So the integral from t equals a to t equals b of u times dv. So remember, u is a height, or I'm sorry, u is a width in this situation, and dv is a height. So what we need to do is interpret, what does this mean, u times dv? Well, this is a width times a height for a very thin little rectangle. Where is that rectangle? Well, since t is going from a to b, right, we're going to get all of the u values from a to b, and all of the v values from v of a to v of b. So we need to draw this rectangle for every point along this graph. And these rectangles are going to have width u and infinitely short height. And those rectangles fit like this. Each of these rectangles has width u and height dv. And when you add up the areas of all of these infinitely little rectangles, infinitely many little rectangles, right, that's what this integral does. It adds up all of these areas. What you get is the area of this shape, right? This shape up here. Okay, so now let's look at the other pieces for integration by parts. The next piece, I guess, is u times v evaluated at t equals a and t equals b. Well, let's write out what that is. So this is u of b times v of b minus u of a times times v of a. Okay. Well, look, here we have a product again. U is a width and v is a height. So this is width times height. Both of these are width times height. But width times height of what? So the second one is u of a times u of v. So that's this rectangle down here. Okay, what about u of b times v of b? Well, in this diagram, there's a rectangle that measures u of b wide by v of b tall, and it's the whole rectangle like this. So that's this big rectangle. And when you subtract the two, what you get is, this is going to be a little bit hard for me to draw, unfortunately. When you subtract the two, I don't know what color to use, you get this kind of shape, right? Because it's the big square here, it's not a square, it's a rectangle. The big rectangle minus the small rectangle in the corner, right? And you can see that shape up here. It's this L shape to the upper right of the green rectangle. Okay, the last piece in integration by parts is the integral from t equals a to t equals b of v du. So what is this? Well, this is the sum of infinitely many tiny rectangles. So let's figure out what are these tiny rectangles. Well, v is a height, du is a width. So we're looking for rectangles that are v high and du wide. And here they are. Right? Each one of these rectangles is v high and du wide for a different value of t. Right? Each of these yellow strips has a different value of t from a to b. So this entire integral adds together all of the areas of these strips, so it gives us this area. So integration by parts says that if you start with this rectangle with a hole with a corner cut out, and you subtract away this bottom right-hand piece, what you're left with is this upper left-hand piece. And geometrically, that's kind of obvious. So integration by parts has a really nice graphical interpretation just in terms of areas. You do have to be a little careful to set up everything just right to get this to work, but I think it's kind of neat that there is a picture that you can draw for a formula that looks as weird as integration by parts.